answer that you give is correct. But this is A, this is B. Okay, he said that no, you put A, so which is wrong anyway. So no, the second one is like this. This is wrong, this is correct.
Yeah, I meant the left one.
You meant the left one, but this is true. This is into A. Into A. This is into A.
Oh, okay.
He said, if you the wrong answer, he cannot give you marks. Okay, welcome. Yeah. Alright, then the other person who just comes in, has anybody just comes in about the one that not marked? Huh? Okay. Then another thing that arises, a lot of people looking at, I think it's question 3, okay, saying that, hey, how come I thought it is perfect conductor, I thought it's perfect conductor. Now, don't think whether it's perfect conductor or not, okay? If the question says it is perfect conductor, then it is a perfect conductor. But if the question says there is a volume charge density of 3 coulombs per meter cube, this is definitely not a perfect conductor. Okay, because if there is a surface charge density, that means within that volume there are charges. Now, there cannot be charges inside a perfect conductor. Okay, because no charge, no electric field inside a perfect conductor. So if there is a volume charge density, it is definitely not a perfect conductor. Now, what happens if, let's say, if there's a surface charge density coulomb per meter squared, then it can be either a perfect conductor or a non-perfect conductor. Alright? Either or. Either or. It can be, there can be charge density outside here, can be a perfect conductor or non-perfect conductor. But in this case, most of the time, it is a perfect conductor. Alright? So, this one, you have to be very careful, especially if there is a charge density, volume charge density, it is not a perfect conductor. Alright? That one must be sure about that. Okay, so today we are going to continue with propagations in lossless media to lossy media. Okay, and this Friday we are going to cover tutorial 6, and this Saturday there will be a remedial class. Alright, right here. Okay, 10 to 12, just a reminder. Alright, if you wish to clear doubts, we will cover all the way from right from the beginning. Okay, elementary, volume, surface, and then electricity, magnetic field, and so on. We just progressively, class by class, cover all of them. Alright, so here, 10 o'clock this Saturday. Now, alright, so what have we done with the propagations in free space, lossless medium, and what have we done? Okay, for propagation in lossy medium. Now, we say that we have manipulated the Maxwell equations, okay, to the form of Helmholtz equations. Okay, to the form of Helmholtz equations for propagations in the lossless medium. Now, and we say that in the lossless mediums, what are the possible solutions? Okay, the solutions of an electric field would be something, it has a polarizations, we don't know what, somewhere in general. A magnetic field, okay, and in phasor form, it is j omega t plus j omega t, okay, plus j omega t in minus j k dot r. Okay, for propagating in the k directions. example is, if it is E minus jkz, let's say, then the propagation is in the plus z directions. If it is E plus jkz, then the propagation direction is the minus z direction. Alright? And in the instantaneous form, it is just simply converting, there is an EK5 sometimes, so signify that the phase is not 0 at time t equal to 0 and z equal to 0, or origins. Okay? It is basically the cosine, or the real part of this whole thing, cosine omega t minus k dot r plus phi. And remind you that this thing must be a cosine, cannot be a sine, and this one must be a plus. Okay? If this is not a cosine, or the omega t is not a plus, you are to convert it into a cosine and plus in order to convert it into a time harmonic form. And for magnetic field, it is also very simple. H is just simply equal to H polarization, H naught, and the rest just the same. Everything is the same. You can see that everything is the same. In fact, you can just copy the whole thing down. Okay, so H is equal to H naught cosine plus omega t minus k dot r plus phi. You can see that it is exactly the same, no change. Alright, and the relationship between EH and K is EH and K, the tree will form a right-hand orthogonal coordinate systems. Okay, and what is this K? This K is just equal to the unit vector in the K direction. So this is equal to K over K. Alright? And of course, this K is equal to Kx x plus Ky y plus Kz z. And the magnitude K is just equal to square root of Kx squared plus Ky squared plus Kz squared. Alright? And the relationships between E naught and H naught are just E naught over H naught is equal to 5 naught equal to 120, other medium also equal to square root of mu epsilon. Alright, when epsilon equal to epsilon naught is equal to 120 pi. Now, also the relationship between EH and K is equal to, E is equal to zeta times H cross K. H cross K. And H is equal to 1 over zeta, which is smaller. Remember, H is always smaller than E. Alright? Which is equal to K cross E. Circular. K cross E. Alright? And what other things do you need? K is equal to omega square root of mu epsilon, which is equal to 2 pi over lambda. That's what you need. V equal to F lambda, this is what you need. And from there, the derivative, the other equations, these two equations that can be derived from the other equations are this. You can see that everything else is the same as long as you have a epsilon r, the velocity is slower, the wavelength is shorter, the impedance is smaller by square root epsilon r. So everything is the same. Alright, so, and, alright, you are not required, okay, you will not be asked to, there are some people who ask me, alright, okay, whether this thing need to be memorized or not, need to be used or not, no. Need to use this or no, answer is no. Alright, need to derive this thing or not, the answer is no. Okay, you are not required to derive all these things. No, no. You only need to apply this one. Alright? And the kind of things that you do, you need to apply will be similar to the tutorial. Okay, the kind of tutorial. Write this, find E, find H, find this, what is a what form, what's a wavelength, what's a frequency, and so on and so forth. Okay, so all these derivations, the answer is no. Okay, you are not being asked to derive, but this is there to let you know where are all these things comes from. Alright, where are all these things come from? Now, then what is the lossy material? Now, similarly, you see, just like over here, if it is free space, everything is mu naught epsilon naught, then you get a set of things. And when you come to permittivity, it's no longer mu naught epsilon naught, there's epsilon r, so everything is so-called modified by epsilon r. But what happened to lossy media? Now, to lossy media, okay, again, alright, this part of the thing I'm going to block off. Once again, you don't need to, you will not be asked to derive this one, okay? Now, what is this? Okay, how to move from lossy to lossless. To lossy to lossless actually will move from this one. Remember, this is your Ampere's law, right? This is your Ampere's law. Now, then we say that, well, if I apply the Stokes theorem, this one becomes Stokes theorem becomes like this. And if I take away the integral, this will be my Maxwell equations that you see from here. Curl of H is equal to J. Alright. Then we say that, well, okay, this is what we call the conduction current, which is good. Okay, but when there are space where there is no current flow, no conductor, what should we do? There are still magnetic fields, there are all these things. So how should we account for the phenomena? Then we say that, well, there should be a displacement current. Okay, then we say that there should be a displacement current over here. Okay, so this is a displacement current density. Alright, and we have the conduction current density, which is equal to sigma E, and we have the displacement current density, which is equal to del D, del T, which is equal to epsilon del E del T, because D is equal to epsilon E. Okay, and you differentiate E with respect to T, remember, this one becomes J omega epsilon E. Alright, so this one becomes this. Then we say that, well, during lossless medium time, lossless medium, no conductivity. So lossless medium, no conductivity, I get curl of H is equal to JC equal to J omega epsilon E. Okay, because JC is equal to 0, no conductivity. sigma is equal to 0. So from there I derive my Helmholtz equations. From there I derive my Helmholtz equation. But now I got this one. So how? So that means I will have sigma E plus j omega epsilon E. Right? Now how am I going to put this one in the same form as this one? I can put this in the same form by saying that this is equal to sigma plus j omega epsilon E, right? Factorize E. I take the E out, I factorize E. But still not yet the same form because I need the j omega epsilon. So I take this one out, j omega epsilon, which become okay. I take j omega up, epsilon minus plus sigma over j omega. Is it alright? So if I take the j omega out, so j omega epsilon plus sigma divided by j omega. Is it alright? Okay, huh? So that means it is equal to j omega sigma minus j sigma over omega E. Because 1 over j is equal to minus j. Now, so now I have the same form of this one now. I have the same form of this one now. If I call this one epsilon c, then every equations will be the same now when I substitute epsilon c. Initially, this is omega mu naught epsilon naught for free space. Then if there's a dielectric, become omega mu epsilon. Now there's a lossy dielectric, now omega mu epsilon c. So everything else is the same as long as you substitute this omega, this epsilon c into this one here. Okay, you substitute the omega epsilon become epsilon c into this one here. Then all the operations will remain unchanged. Okay, all the operations will remain unchanged. And same as this epsilon c now. Okay, all the operations will remain unchanged. Now, what is the consequence of this complex number here when you put in here? Consequence for this complex number we put in here. Then this k become a complex number, of course, right? So the complex number that you get is equal to beta minus j alpha. Okay, k you get is become beta minus j alpha. Now, so when you do your calculator and when you find k, the real part must be positive, the imaginary part must be negative. If you get the real part as negative, answer is wrong. If you get the imaginary part as positive, the answer is wrong. Okay, you cannot have any other choice, but when you do your complex number, if you got the, don't get this one, your answer is wrong. Go and redo again. Okay, your answer is wrong. Now, why this answer, why it must be this answer? Can somebody tell me? Very simple also. Because initially you have E minus j k z, right? This is a propagation in the plus z direction. So in lossy media, so what? You still have to be propagating in the plus z direction. Doesn't mean that when it's lossy, you have to propagate back. Cannot be, right? So this one must be, if you put it back, E minus j beta minus j alpha z, which is equal to E minus j beta z E minus alpha z. So you see that the wave is still propagating in the positive z direction, does not change. Okay, so if this one become minus, then this one will become plus. Then the wave propagate backward. I mean, which is cannot be, right? Physically cannot be. If it's lossy, doesn't mean that it propagate forward and then straight will become backward. And this one must be negative, because if this is positive, here, this one becomes positive. And what does it mean? The wave, when there's lossy media, that means the amplitude must decay, loss. The amplitude cannot go up. If lossy media, the amplitude go up and the energy get bigger and bigger. I mean, that is not lossy. I don't know where the energy comes from. Cannot be, right? So this one must be beta minus J alpha. You got it anywhere else? Anything else? Wrong. Okay, this is the first thing. Second thing is that over the year I find that a lot of students do not know how to handle square root of either a plus jb or a minus jb. How to handle this one? If your calculator can take the square root of a plus jb, good for you. If your calculator cannot do, how to do it? Again, anybody know? Now, if your calculator cannot do a direct square root of a plus jb, okay, make it equal to magnitude ej theta. Convert it into the polar coordinate. That one I believe that all calculators can do. Okay, do your rectangular, convert to polar. Okay, and the square root means that it is become square root of m, and the phase angle become ej theta by 2. Okay, that is how you take the square root of a complex number. And then you convert it back to rectangular if you need to. Alright? But if you need to take the complex number of a rectangular form, complex number, we convert it to polar form, the magnitude take the square root, the phase angle divide by 2. Okay? That's how you do it. Now, so what are the consequence? The consequence is now k cannot be equal to 2 pi over lambda, because k is complex now, and wavelength is not complex. Wavelength cannot be complex. So now what we have is now beta is equal to 2 pi lambda. We take the real part. Beta is equal to 2 pi over lambda. Okay, so this is another consequence. Okay, then what is the other consequences? What is the other consequences? Remember, now this zeta becomes zeta c because it is now complex. So this is zeta c, this is zeta c. Now previously, you see that this and this is exactly the same. But now it cannot be, because zeta c is a complex number. Zeta c will have a phase angle, right? Zeta c will have a phase angle is equal to zeta c magnitude ej theta zeta. You have a phase angle, right? Because it's now a complex number. Okay? So now, if that is the case, E and H now, this cosine term will not be exactly the same. Because let's say this one is, because let's assume that this is my E, this is where I started. Now, what is my H? My H will be divided by zeta c, but zeta t has a complex angle. Divide by this, that means this one will have become E minus J zeta c. Can you see that one at this point? Can you see that one at this point? Zeta c is a complex value. Therefore, you have a phase angle. Correct or not? Zeta c is complex value, there's a phase angle. 1 over the complex angle become minus j and zeta. Sorry, I write wrongly because no wonder. Okay, theta zeta. Okay, theta zeta. Alright. If that is the case, then this cosine term, so now means that the instantaneous form of the electric field and magnetic field is now no longer in phase. When this one is equal to 0, this is exactly the same, exactly in phase. When this one is not, there is a phase angle. So these are the only difference. Alright? And then what we are going to do today, this is where we stopped last week. Okay, what we are going to do today is go and look at the special cases. Special cases, what are the special cases? Special cases when which one is dominant? Whether the conduction current is bigger than the displacement current, or the displacement current is bigger than the conduction current. Which one is bigger? Okay, so we have a ratio. We have a ratio between this and this. This is what we call the loss tangent. Okay, we have a ratio between sigma and omega epsilon. This is what we call a loss tangent. We say that loss tangent is greater than 1, means that sigma is big. Alright, so this is a good conductor. When a loss tangent is very much smaller than 1, that means sigma is small. That means this is a good dielectric. Alright? But one thing, okay, again, a lot of previous mistake is that this is sigma over omega epsilon. Okay, epsilon, epsilon naught, epsilon r. Alright? In the previous exam, there are some people put epsilon naught, some people put epsilon r, some people put epsilon naught without epsilon r, some people put epsilon r without epsilon naught. Okay, it is a full epsilon which is equal to epsilon naught, epsilon r. Otherwise, you will get, because you see, whether good conductor or good dielectric, you have different sets of equations. If your decision is wrong, because you put the wrong epsilon, you calculate wrongly, you use a wrong decision, you use a wrong set of equations, everything else is wrong. The result definitely wrong, right? Correct? And it can be quite a lot of difference, you know, because sigma over omega epsilon naught is 1 over 36 pi times 10 to the power of minus 9 epsilon r. If this one is not there, there can be a lot of difference in the result. And you will get used to different sets of formulas. Alright. Okay, so this is where we left. Okay. Lossy medium. Alright, remember. Okay. For lossless medium, we deal with, sorry, I write this one wrongly and nobody correct me. This is D, alright? Okay. When we deal with lossless medium, curl of H is equal to the displacement current terms. Okay, now, because of conductivity, the conduction current terms must come in. Okay, conduction current terms must come in. Alright, so you can see that the conduction current terms comes in down here, so you factorize, pick up J omega. Now this is omega C. Okay, this is omega C. Okay, and omega C equal to epsilon minus sigma over omega. Omega C equal to epsilon minus sigma over omega. Okay, and sometimes, which I don't like, okay, some books, and write it as epsilon prime epsilon double prime. So epsilon prime is actually epsilon. Okay? Epsilon double prime is actually sigma over omega. Alright? So I cannot be helped. There are books written right, and there are books which are even more confusing. Is they write it as they say then there's it can be written as sigma naught epsilon naught epsilon r. I cannot remember what's the definition. I think the next slide. Yeah, down here. They have another definition, epsilon RC, you equal to epsilon C over epsilon naught, equal to epsilon R equal to minus J or sigma. This too many definitions. Okay, so they have become an epsilon R prime and epsilon R double prime. You see, as if an epsilon prime and epsilon double prime not confusing enough. Now we have epsilon R prime and epsilon R double prime. Too many definitions. Okay, now this kind of definitions, I advise you to write it in your cheat sheet. Okay, just in case. Okay, just in case that someone lift up a exam question from some book. So we got all this. So just in case. All right. But if not, then not to worry. The important one is the one right at top, loss tangent. Loss tangent is equal to sigma over omega epsilon. This is the one that you have to deal with most of the time because you want to know whether it's a good conductor or a bad conductor. So you have to find sigma over omega epsilon. Sigma over omega epsilon. And that is the ratio between the conduction current magnitude and displacement current magnitude. Because the magnitude of the conduction current is sigma, and the magnitude for the displacement current is omega epsilon. So it's a ratio of the two magnitudes. So when it's greater than 1, conduction current dominate. Less than 1, displacement current dominate. Alright, so that is an important one. Now, as I said, now K is equal to this whole thing. K become Kc. Okay, because epsilon becomes epsilon c. So this is a complex number. And if you don't know how to evaluate a complex number of a rectangular, square root of a rectangular form complex number, do it by magnitude and phase. Alright, so now K equal to beta minus J alpha has to be like that. Okay? Has to be like that because if you get anything wrong, plus, minus plus, or whatever, any other combination, you press the calculator wrongly. Alright? Okay, so now Kc now becomes this one. Kc now becomes like this. So the wave is still propagating in the z directions, but the magnitude is also decaying. So it's propagating, but the magnitude is also decaying. The rest are the same. You see this one propagating and decaying. So Kc now become Kcx, Kcyy, Kczz, and so on and so forth. Everything else still the same. This set of equations still the same. EHK, EHK, EHK. So this tree is actually one equation. Okay, this tree is actually just one equation. Just rotate. Where is it now? EHK, EHK, EHK. Just rotating this is the rectangular coordinate system. These sets here, okay, down here. Yeah, down here. Okay, these two down here, which is exactly the same. And zeta c, you can see that it's complex because of this one. Now it has a complex angle. Now this one has a complex angle. And this complex angle will account for the phase change between electric field and magnetic field. Alright? Excuse me. And you can see down here, this is the phase angle difference between the electric field and magnetic field. You can see that everything is the same, but now the phase angle angle is being introduced. Okay, the phase angle is being introduced down here. Alright. But what happens if I give you h without the phase angle? What happens if I give you h without a phase angle? Let's say, assuming that this one, because you are so used to see this one, electric field with no phase angle, h got phase angle. But what happens if I have h got no phase angle? Then the electric field will have a phase angle. Because this one here, you see? Because these equations. Because it is equation. If h original got no phase angle, because of this, then electric field will have a phase angle. Alright? So it's either this is 0, this is minus theta n, or this is 0, this is plus theta n. Either way. So the phase angle is always theta n. If electric field has 0 phase, magnetic field phase angle is minus theta n. If magnetic field 0 phase angle, electric field plus theta n. That's all. Okay, so yeah, that's the difference. As long the difference meaning that. Okay, now you know what is the difference mean. Okay, I don't have to try to explain difference. Okay. Okay, and this one you see lossless medium is a special case when alpha equal to 0 and theta n equal to 0. So lossless medium is a special case of a lossy medium with alpha equal to 0. Okay, alpha equal to 0 and theta n equal to 0, sigma equal to 0. It's just a special case. Alright, so this is a propagation. Okay, now this is where we left behind and this is where we start. Okay, did we stop here or did we? I think we went further than this one. Okay, we went further than this one. Okay, so now you look at the loss tangent. When the loss tangent is greater than, very much greater than 1. Now, don't ask me what happens if it's equal to 4. Does it count greater, very much greater than 1 or not? Alright, normally, okay, when we say very much greater than 1, I think we are saying that it's at least a few tens. Okay, a few tens or 100 or at least, I don't know whether 10 count or not. Okay, alright. Now, of course, if it is either here or there, let's say this is equal to 3 or 4, then sorry, you cannot classify them as either a good conductor or low loss dielectric. That means it will be a general lossy medium. Okay, general lossy medium. To classify this one normally will take that in terms of 100, and this one have to be in terms of 0.01 or below or something like that. Alright. Okay. Now, these are the simplified forms. Okay. Now, this is a general form when it's sub in here. When you sub this one in here, it's going to be a complex. It looks complex. Okay. Where can I? Okay. Okay. It will become like this: omega square root of mu naught epsilon naught epsilon r minus j sigma omega. Okay, it will become like this. Omega mu epsilon c. Mu epsilon c. I put mu naught here because normally, for your case, mu I equal to 1. Alright, so become like this. Now, so this is equal to beta minus j alpha. Okay, the equation sheets, okay, will be given to you, of course. Okay. Now, in case that where this is very much greater than 1, in the case that where this is very much greater than 1, we can once again applying binomial theorems, binomial theorem, and throw away the terms and all these things. And it so happens that alpha is equal to beta. The magnitude of alpha is equal to beta. Okay, for a very good conductor, alpha is equal to beta is equal to square root of pi f mu sigma. Okay, pi square root of pi f mu sigma. And the phase, and this zeta c is equal to square root 2 of alpha over sigma, and the phase angle is pi by 4. Okay, happens that, okay, these equations should also be given in your exam, I remember. Alright, so alpha and beta are the same. and the phase and the magnitude square root 2 alpha sigma e pi by 4. Now, the reason why, that's why I say that this ratio, you have to be very, very careful, sigma over omega epsilon, because you can see that when it is very much greater than 1, you have one set of equations. And later on, if it's not greater than 1, you have a different set of equations. Alright, if you this one, you starting one, you calculate wrongly already, after that all the equations, you apply the wrong set of equations, you definitely get the wrong answer. Alright, so that goes without saying already. Alright? And the phase velocity, okay, which is equal to omega beta. Okay, sorry, this is the part that I probably missed out. You said, okay, the velocity, I beg your pardon, velocity is equal to omega over k. Alright, velocity is omega over k. So now the velocity is equal to omega over beta. Just like wavelength. Okay, just like wavelength. Wavelength is real. So wavelength cannot be equal to a complex number. Same thing, velocity is real. So velocity cannot be equal to a complex number. V equal to omega k cannot be equal to so it's omega beta. Okay, actually, this one can derive from these two also. I mean, all these equations are all related. Alright, all these equations are all related. So, velocity is equal to omega over beta, and wavelength now is equal to 2 pi over beta. You can see that they are now different. They are now different. The wavelength is depending on the conductivity. The wavelength is depending on the conductivity as well. Now, in a good conductor, because of attenuation constant, okay, so in a wave, this thing will attenuate like this. Okay, attenuate like this. This one, somebody asked me a very good question. I think I now remember we have done this after the class. He said, okay, I say that, well, I say that now for a DC current to flow through, okay, to flow through the wire, the current occupies the entire cross sections. Okay, but now because of the skin depths, okay, we will flow only across these cross sections. Now the question is now if, I mean, which direction is Z, never mind. Let's say Z is going to here, the current going there, should not be the current will attenuate like this in the Z direction. And why is it attenuating in this direction and not that direction? The answer is basically there are two phenomena here over here. Okay, there are two phenomena over here. Now, one phenomenon is that the current flow. Okay, the current flow, how is the current flow? The current flow is because there is a potential difference, right? You actually force the electron going through. So the electron through this one is being forced through, and the attenuations to that current flow is the resistance. This is your Ohm's law, cannot change. Okay, the voltage across the cable, is the force that's forcing it through. So the current flowing through, and it is the resistance that is attenuating. And what is the resistance? Is it the resistance of the whole cable, of the whole surface, or resistance over here? Ohm's law never say. So it's a resistance. Now, but in that case, this one does not apply because there is a continuous pushing of the electron down. Okay, continuous voltage pushing the electron down. Now, then why is this one? Because basically, when you have a charges, remember when you have charges, Gauss law, right? There is electric field, right? You still remember your Gauss law, I hope. Okay, when you have Gauss law, you have electric field. Okay, and these are the electric field. These are that one that's pushing this one to the side. So there are two things. Okay, one is in this direction, you have an electromotive force. In that direction, you have no electromotive force in that direction. So these phenomena will catch up with you in that particular directions. All right. Okay, so now we also say that because of this, your computations for attenuation can be seriously wrong. When you do DC at 1 megahertz, you know that it's already 8 times difference already. What happened to 1 gigahertz? 1 gigahertz will be 8,000 times different. I know, so your calculation will miss by 8,000 times. That's a serious number. Alright? And we also said because of this, the reason why communications, RF radio wave communication in seawater cannot work, and so on and so forth. And we say that for perfect conductor now, perfect conductor, the skin depth is equal to 0, and that's the reason why for perfect conductor, remember, just right from the beginning I said that there is only surface charge density. Current only flows on the surface, charge only residing on the surface. And if the question tells you there is a volume charge density, then it's definitely a non-perfect conductor. A non-conductor, by the way. Okay, if a low-loss dielectric, that means the loss tangent is not very much smaller than 1. And once again, applying your binomials theorem, okay, now your K is equal to this value. Now, it's a different set of value now. Alpha is no longer equal to beta. Okay, this is beta minus J alpha. Beta minus J alpha. Just now beta is equal to alpha. Now beta is not equal to alpha. Alright, so once again, remind you when you calculate this one, calculate correctly. Okay, you use the wrong sets of equation, nobody know how to give you marks. Alright? Okay? So alpha and beta are not the same. Zeta is the same as zeta is before, but the rest are the same. You can see the same zeta, lossless case, same velocity, lossless case, same wavelength, lossless case. But alpha is not the same. Beta actually is the same. Beta is the same K as the lossless K. But so for low loss dielectric, everything else is the same except that you have a alpha. So this is attenuating. And when you have alpha, you have a skin depth. Wow, okay, this set of equations I believe is given in the exam. Okay, once again, alright. Pick the right sets of equations. Good conductor, loss tangent very much greater than 1. Low loss medium, loss tangent very much smaller than 1. Lossless medium, loss tangent equal to 0. And if loss tangent equal to 2, sorry, got to use this one. Alright. And how to use this one? Remember the square root, Okay, this square root is okay. These are the all the real number. Okay, these all these number, but this is not. Alright, remember how you take the square root. And epsilon prime, epsilon double prime, once again, what is epsilon prime, what is epsilon prime? Epsilon prime is equal to epsilon, which is equal to epsilon naught, epsilon r. Epsilon double prime is equal to sigma over omega. Yeah. Epsilon double prime is sigma over omega. Okay, it's given here, so now. Oh yeah, this, okay, it's also given here, 100 and 101, so okay, no problem. So this table is given in exam. Okay, that's good. This is where we stopped last week. So we can now start looking on the examples. once again, Friday we will do tutorial 6, Saturday we have a remedial. Electric field intensity of a linearly polarized uniform plane wave in a plus Z medium in the seawater. Okay, so now I have E is equal to X 100 cosine 10 to the power of 7 pi t and Z equal to 0. Hey, this question is very tricky. Z equal to 0. So this one should have a minus j k z. Right, if propagating in the plus z direction must have minus j k z. By the time z equal to 0 is equal to this. So this z equal to 0, yeah, what? Z equal to 0, k times 0 is 0. So it becomes like this. Oh, so a lot of people just write like this and then, after how to convert? Oh, your standard form has this one. Your standard form has this one. Okay, your standard form has this one at z equal to 0. Now I don't know whether should I need a plus 5 or not. I don't know, write down first. Now, but also remember one thing. Just now when I write E for a lossless medium, I write like this, right? I write like this: E j omega t E minus j k z E j phi. I write like this, right? Okay. Now, but if k become beta minus j alpha, that means I should have E naught E j omega t E minus j beta z E minus alpha z E j phi. Right? I should have that one, right? So in that case, I should not write like this. I should write beta. Okay, beta. Because it's very tricky. If put z equal to 0, the j beta disappeared. But I also have a alpha. E minus j alpha z. And if z equal to 0, E minus j alpha z also equal to 0. Correct or not? That's why this question is tricky. They're supposed to have like this. So I have to write my full instantaneous form like this. Or not? Because when z equal to 0, e to the power minus alpha z also equal to 0. Minus j beta z also equal to 0. If you are not careful, if you don't write all this, don't write the full story out, everything else is gone. Okay, then epsilon I equal to 72, mu I equal to 1, sigma equal to 4, sigma. Determine attenuation constant, intrinsic impedance. Okay, so now, first thing first. Which formula do we use? Sigma over omega epsilon, which is equal to 4 over, what is the frequency? Omega is 10 to the power 7 pi, right? So this is okay. You see, 10 to the power 7 pi times 1 over 36 pi times 10 to the power minus 9 times 72. Okay, what is this value? I don't know. So, see. 200. Okay, so it's equal to 200. Greater, very much greater than 1. So, okay. So now, what is the attenuation constant? What is all this? Establish this one. So now, my alpha is equal to beta for good conductor, which is equal to pi f mu sigma. No sweat. Attenuation constant, intrinsic impedance, zeta is equal to square root 2 alpha over sigma ej pi plus 4. So this one okay, this one okay. Right, those are right set of equations. Phase velocity V is equal to omega beta. Okay. Skin depth del is equal to 1 over alpha. Okay. So no issue. So as long as you get the loss tangent correctly, you use the correct sets of this one, you get the attenuation constant, you get the intrinsic impedance, you get the phase velocity, you get the speed depth. Okay, so yeah, it's all here. All right, it's all here. I mean, the equations are all here. Alpha equal to beta, this one is zeta c equal to up r delta, everything all there. No? Okay? So that is not an issue. The important thing is get your loss tangent correct. If you use the wrong equations, you can't do anything. Right expression for hzt and EZT. Okay. That is an instantaneous form. Okay, so this is my instantaneous form. I have the alpha, I have a beta here. I have beta here, I have alpha here. No problem. Alright. So now, what is that? Phi I don't know. I'll just leave it there. No worry. Now, then what is H? H is equal to 1 over zeta c k K cross E. Alright, so you can do this one quite easily. Okay, now again, okay, you can, the safer way is to convert it into phasor form and then do this and convert it back, or do both. Alright, the quick form is actually, if you look at this, I can write it down also. No big deal. Okay, if you want, you can convert it to phasor form is equal to E100. Now, phasor form, remember, this one must be there, and then this whole thing Ej omega t E minus j beta z Ej phi. This one does not matter because cannot calculate it. So if I leave it there also can, don't leave it there also can. So this is equal to what is my pi? Okay, it's pi. Pi Ej pi by 4. K direction is Z cross the whole thing. Okay, so this one is equal to what? 1 over pi E minus j pi by 4. Z cross x give me what? Y, right? Z cross x give me y. So this one whole thing becomes the same 100 E minus alpha z Ej omega t E minus j beta z Ej phi. Alright, so there you go. Okay, and then the next thing is write it back in instantaneous form. Now, instantaneous form, you only take the real part of all the e to the power of j something. Okay, only this one involved, this one involved, this one involved, this one involved, but this one not involved. Alright? So you're going to remember when you take the real part, you take the real part of Ej something, E minus something, the one not involved. So this one becomes y 100 over pi E minus alpha z cosine omega t minus beta z minus pi by 4 plus 5. There you are. You can see that the phase difference between this one and this one. Okay. And you are smart enough, okay, you can see that this instantaneous form and this instantaneous form, I can actually write them exactly the same thing. Okay, E minus alpha z is the same. The cosine is the same. I just add the phase. I add the phase difference inside there only. Then the magnitude E naught over H naught is equal to zeta. Magnitude is the same. E cross H is equal to K is the same. So if you are quick, you can write it down directly. But I would advise that, okay, for those of you who are not 100% confident, write down the phasor rule, the cross, and then convert it back, because even if you got it wrong, at the end, okay, you get your partial credit. And you might be, let's say whole thing is 10 marks. If you do this, do the cross, do that, you might get up to 8 marks. Alright, even if the final answer is wrong, because we look at all the steps which are correct, we'll give you 8 marks or so. Alright, but if you do straight directly, I mean, you're 100% confident, go for it. Okay, save you 5 minutes. And if not, okay, you might get, if you got it wrong, just check. Probably right, probably wrong, you probably get another 5 marks instead of that. Or even less. So, if you're 100% confident, do so. If not, do it step by step. Okay, find the distance Z1 at which the amplitude of the electric field is 10% of its value. I mean, this is very simple. Alright, so what does it mean? It means that 100 E minus alpha Z is equal to 1%. 1% is 0.01, right? It's 0.01 times 100. The distance Z1, at which the amplitude at distance Z1 is equal to 1% at Z0. At Z0 is equal to 100, right? So this one is equal to this one. Okay. Distance Z1 at which the amplitude of the electric field, distance Z1, the amplitude of electric field. What is the amplitude of electric field? Is this one. This is the amplitude of electric field. The rest are phase. Okay, the rest are phase. The rest are phase. The amplitude is this one. So at Z1, the amplitude of the electric field is equal to 1% of the value at Z equal to 0. Okay, at Z equal to 0 is 100. Okay, so you can find Z1. Compute the skin depth at a frequency of 1 gigahertz. I think this is very simple. Alright, skin depth is here. You just compute it at 100. Sorry, at 1 gigahertz. What is the skin depth? The skin depth del is equal to what? 1 over square root of f pi n mu. So f is here, alright? Pi n, the skin depth is 1 over square root of pi n mu sigma. Your f is 1 gigahertz. So you can compute very simple, very easy. Alright, so this is this is what it is, okay. Do the conversions. Okay, I'm wrong. Sorry. You see, I have made a mistakes. But just now when I do it at that frequency, okay, I do it at that frequency, at this f equal to 5 times 10 to the power 6, at this one, at this frequency here, okay, at this frequency here, this is omega, omega equal to 10 to the power 7 pi, f equal to 5 megahertz. Okay, at this frequency I calculated this one, which is equal to 200, which is very much greater than 1. So I use this set of formula. I find the skin depth using this set of formula. No sweat, right? But the trick here is that I fall into this trick also. At 1 gigahertz, I got to recalculate the loss tangent, because loss tangent is a function of omega. I forget to calculate recalculate the loss tangent. So I use the wrong set of formula. I say, oh, this is like that, just put one finger wrong. Huh? So you can see that I also make mistake. Okay, so you have to recalculate the loss tangent. Now loss tangent is only equal to 1. Oh, so sorry. So you got to use different sets of formula for your steam gap. Alright. So you see, so easy to make mistakes like this. Alright. Alright, any questions? Any questions? No. Pointing vectors. Ah, yeah, this is a difficult one. Alright, this pointing vector come up quite often also. Not this slide, but the examples. Okay, the example that one come up quite often also. Alright, do you need a rest? Okay. Now, basically, what does it mean? Okay, what's so important? Why everybody want to go out? Need a break? Sorry. Okay, go. Bear with me, only do 1, 2, 3, 4 more slides. And you can all go home already. I can't go home yet. Yes. I have night class, yes.
Do we still have quiz?
Sorry?
Do we still have quiz?
Yes, there's a, oh, today ah?
Yeah.
I might. I don't know. Let's see how much time do I have. Let me see how much time do I have left. A quiz is, may I ask you, quiz, don't go and look at your friend's solution. Yeah, but if I want to discuss and then until you're convinced that that solution is correct, but don't copy other people's solution. Then, no, it's a way to learn also. No. If the frequency never change, yeah, if the same stay as the same, yeah, that's fine. Because just now you already calculated already. And that frequency already. In fact, almost, you see, perfect conductor is another special case. We are not lost in medium to say that the conductor by minor conductivity. Not perfect. But why for lost lost in medium to line zero, they are two extremes. Two extremes. Because one is in perfect conductor, the loss tangent is okay. For lossless medium, the loss tangent is zero. It's also two extremes. Because when you have sigma, when you are conducting, when you have receiving, when you are receiving, okay, the question is that why there's such a, why conductivity is equal to zero? Why conductivity equal to zero? Okay, it is lossless. But conductivity equal to infinite, which is a perfect conductor, it is also lossless. Yes, because when a perfect conductor, perfect, there's nothing. Because basically, remember we said that there are two components. One is displacement, one is conduction current. Okay, only when only one of them present, the other one not present, then is perfect. Then is fully lossless. Perfect dielectric. Okay, conductivity sigma equal to zero. Now, and then perfect conductor J is equal to sigma E. How do you write this? That means current can flow without electric field. Because sigma, what do you mean? When sigma equal to infinity, how do you do that? Okay, so you got to see that they are two extreme cases, alright? Only when both of them are present is a lossy medium. Alright, I think go back to think about it. We have to continue. Okay, now pointing vector. Pointing vector is half of real E cross H conjugate. We know that. Okay, half of real is E cross H conjugate. What's the difference between this one and the lossless medium? Nothing. The important thing is this factor, because E got the E minus alpha Z, H also got the E minus alpha Z, so that the two multiplied by together is E the power of minus 2 alpha Z, right? So the power is lost by E the power of minus 2 alpha Z. As is decay is equal to loss is equal to square of E minus alpha Z squared. Alright? Electric field attenuate like this, magnetic field attenuate like that, the power of God squared, right? Okay, that is the only big difference. The other minor difference is that now the zeta is replaced by zeta C. Now, it's not often when I see exams question to ask you to evaluate this one. But in the rare occasions that I see, the mistake is always like that. Because zeta C is a complex number. Okay, zeta C is a complex number. Now, So A plus JB. What is the real of this one? A lot of people give me 1 over A. Very wrong, huh? Very wrong. It's not equal to 1 over A. Okay, this is equal to, you got to multiply top and bottom, become A squared plus B squared, A minus JB. You can multiply top and bottom by A minus JB. Yeah? So this is equal to A over A squared plus B squared. So the real part is equal to this one. Alright? Real part is equal. But this one seldom comes out, so not be too worried. Okay, let's look at example. Alright, for the plane wave in example 1, find the power density at distance of skin depth Z equal to del and Z equal to 0. That is no problem. Okay. Example 1, this is my E, this is my H, this is my skin depth, this is theta alpha. So what's so big deal about this one? No big deal, actually this one. Okay. Because of this factor, okay, when it is at Z equal to 0, it is 1125.4. Okay, when Z is equal to skin depth, this is equal to 153.62. You can see that these two, the ratio between these two value is actually equal to this one. The ratio between these two values is actually equal to this one. The difference is only this one. So this is just a very simple. That is just a very simple example. The power at this point and the power at that point is actually modified by that particular value. That's all. Okay, last example, I think. For the plane wave in example 1, assume that the average power density at Z equal to 0.5 is SAB. Find the locations, i.e. the value of Z at which the average power density is 0.0. Well, this is you got to understand how is the problem phrased. Alright, sometimes if you are not clear, you might misunderstand the questions and you might get the wrong answer. Okay, this is Z. At Z equal to 0.5 meter SAB. Okay, you want to find the locations of Z at which the power density, let's say Z is here, this is 0.0001 SAB. Alright. Now, if you do not understand this ratio is all about, okay, I would suggest that you write at Z equal to 0, it is called SAB naught. Now, at this point here is SAB naught, E minus 2 alpha times 0.5. Remember, when we propagate, the SAB drops by e to the power of minus 2.5. So at this point here is SAB naught, E minus 2 alpha Z. Okay, so if equate this one is equal to SAB, this one is equal to 0.0001 SAB, you can find Z. Okay, so this is what this ratio is all about. Okay, this is what this ratio is all about. Or if you put Z equal to 0.5 plus Z1, if you put Z equal to 0.5 plus Z1, you can actually do this directly. But if you are not, you don't see the clever one, you just do it by the simple systematic way. SAB is 0, so when you propagate down, you must go by e to the power of minus 2 alpha Z. Alright? So you just solve for these two equations. you solve for these two equations, you can see that SAV naught is cancelled off. Okay, SAD naught is cancelled off, and everything else is cancelled off, and you can bisect. So you can do it this way, or you can do it that way. Alright. But the main thing is that the power density decay by e to the power of minus 2 alpha z. That's all. Alright, any questions? Okay, it seems that we do have time. Alright, just now somebody asked me whether have any class test or not. I said depends on whether I have time or not.
Hi.
Yeah.
Hi.
Now it's a good one for you. A perfect conductor is lossy or lossless? Just like that. So try to answer this one. And remember, Friday we will do tutorial 6 and Saturday a remedial right here, 10 o'clock. Alright? Tuesday is my best day. Tuesday. After this, I will take a rest, take dinner, and go to my class. Yeah? Sorry? Saturday, I'm going to start right from the beginning. Right from the elementary, volume, elementary, you can see that for one there can be more than one answer, okay? Because one is frequency, one is conductivity, so there can be more than one answer. Possible. Yeah. Because one is frequency and one is conductivity. I mean, there can be only one answer. Let's say if the skin depth does not change with frequency or conductivity. You got great sign, you got perfect great sign, it's not the same, right? Chong okay, just a few more months. By the way, Saturday in media class no test. No class test on Saturday. It's voluntary, not compulsory. So. Okay or not? Can we close out? Question 1 is from questions. You just look from the question. From question 2, I say so many times already. But question 3 is probably the one that you are thinking. But just now that gentleman already asked me the questions. I already actually reply with the answer already. So I know. Question 1, you look at the formula. Question 2, I emphasize so many times down here.
sigma 这边是这样子，它是5万这边的话，它这边的都是它这边直接成功。对，必须要。
Alright, can we have it back? Okay, thank you very much. Cannot come down, I still got night class tonight.